Okay, so this video is on continuous charge distributions. So this is probably the hardest bit of homework 2, and it's among the harder skills in the class. So this course really kind of gets off and running here pretty quickly. So in homework number 1, we had a single point charge, and we might want to know what's the electric field it makes over here. And so for that, we need to know how far are we away. R, it's a positive charge, so it makes an electric field that points radially away. And the formula which gives that is this. And so we might have 1 or 2 or 7 of these charges, and they all make contributions to this point in space, and we find the net electric field by just doing the vector addition of those. So that's for kind of discrete or countable point charges. But on this homework, what we're going to do is we're going to turn charge into a continuous medium, kind of like charged butter or something like that. They'll kind of smear all around the place. And so here we have some object where we still have a total charge plus Q on it, but that charge is kind of spread out all over the place. And then the question becomes, how do we find the electric field of something like that? And so what we do, this is not like you can just count this is a continuous distribution of charge. So how might we find the electric field at some point away from here? And so what we do is we say, okay, well, each tiny little bit of this charge, we'll say dq, can be treated as a point charge. And so here, same thing, we're a distance r away from this particular point charge. The electric field will be radially away since it's a positive charge. And the only difference is we call it dq instead of q because this is just one bit of the charge. So we use the same formula but adapted. So k times dq over r squared in the r hat direction. And we don't call the result E because it's not the electric field of the whole thing. It's just one tiny bit of contribution to the electric field from this one little part of the object. And so we're going with this, as if you probably can guess, we are simply going to integrate all of these into the overall electric field. So we basically combine all these little dq's. There might be a different dq over here, and that particular dq might be a different distance away from our point in question. If it contributes really away, that'll of course be in a slightly different direction than the first one. And so the question is, how do we execute on the math to do that? And so first, I'm just going to kind of talk about the language that we're going to use for this. In one dimension, we can just start there. Let's say we smear the charge out along a single axis. So we have to take a total charge plus Q, and we smear it out along a distance length L. And we can, of course, start by doing that kind of evenly or uniformly. So the charge isn't bunchy, it's just kind of the same everywhere. And we can define a quantity where the total charge over the total length, we call that lambda, the Greek letter lambda, and that is what we use for one dimension. This is called linear charge density. So the units of it would be coulombs per meter. So it's not density in the sense of how I used it in physics 1. This is coulombs, not kilogram. It's not mass density, it's charge density. And this is so far only along a single axis. And so it's just linear density. And so if someone gave you, just inverting this equation, if someone gave you the lambda for a particular line and you multiplied it by the total length, it will give you the total charge. The coulombs per meter times how many meters it actually is would give you the total coulombs. Now you can certainly do this as well for a non-uniform charge distribution. So let's say you had the same line of length L, same Q total on it, but you decided you're not going to smear that charge evenly. It's going to be pretty thinly spaced over here, and then you're going to smear your charge butter much more heavily on the bottom part, let's say. And so if we look at this, if there's a small length dl over here that we're examining of the whole thing, and a same small length dl over here, they're not going to have the same amount of charge on them. If we basically use the infinitesimal version of this, both of these bits of length will also have a small bit of charge. So this will have a small bit of charge dq along this length right here, whereas in the same bit of length you have, of course, much more charge, and I'll try to write that as a big dq. And so you can see if the denominators are the same dl, but this one has more charge, this will result in a larger lambda over here, and this the charge density is lower, smaller lambda. And so you can see that lambda now becomes a function of where you are along that. So lambda is essentially now a function. So what would you do? Well, you just invert this relationship, dq equals lambda dl, and then to get the total amount of charge, you're just going to, of course, integrate all your dq's up, add them all up, and this results in this equation, integral of lambda dl. And that's the most general relationship for how to find the charge on any object, with lambda being possibly a function of L itself. Now, if lambda were not a function, but it just came out of the integral, you could see what would happen. If it came out, because it's not actually a function, it's a constant because it's uniform, then you get lambda integral of dl is just, of course, the whole length, and we are back here. That's a special case. This is the more general case. We'll focus mainly on uniform charge distributions in this class. We will see a few non-uniform ones here and there. Generally speaking, the functions I'm going to make are pretty easy to integrate. Just remember to leave it inside the integral if it is a function. Same idea. We'll actually do similar integrals, not for Q itself, but also for the electric field and even voltage as we get to homeworks 3 and 4. I haven't even told you what voltage is yet, but just remember the same strategy. If it's a function, lambda is a function, leave it in there, integrate it along with whatever other junk might be in there. If it's constant, you can pull it out. Now, same idea if you're in 2 dimensions. So let me try to make this kind of a table here. In 2 dimensions, same idea. We're just going to use a different Greek letter. We're going to use sigma for area charge density. This is when we are spreading the charge in 2 dimensions, kind of like a weird piece of toast. We're spreading it across an area A. And for a uniform distribution, you've buttered your toast nice and uniformly. You can just divide the total charge over the total area. That is the sigma that is across your entire object. Units would be coulombs per meter squared now. And likewise, you can invert this. If you want the total charge, multiply sigma times the area. And if it's non-uniform, if it's bunchy, then same deal. It's going to be a function that you have to leave in there. Now you might look at the dA and go, is this going to be a double integral? Certainly it can be. I'll leave that kind of trickery for math class, but we'll try to leave this and have this be not totally just a random charge distribution, so that we can really do this as a single integral, and because the other one, other dimension will be very symmetric. So we'll try to keep the math to a minimum while just kind of examining the ideas. And then finally, I'll see if I can squeeze it in here on the bottom. For 3D, we use rho, which is volume charge density. And same idea, you're just distributing the, some weird shape. I don't know how to draw in 3 dimensions, so I'll just kind of draw it, try to show that. But you have a total charge Q distributed in some total volume V. And if it's uniform, which is this left-hand column here, you just rho equals Q over V. Units would be, coulombs per meter cubed. This one you have to be especially careful because we do use rho for mass density as well, but in this class we're pretty much using charge density only. And then if it's non-uniform, same deal. It's a function of where you are along the object. You have to use rho. Now this could potentially be a triple integral. I'll tell you right now, we're not going to do any integration of three-dimensional charge distributions here because there's only so much you can do to make these simple. So I'm going to wait till homework 4 to tackle any of these, any of the three-dimensional charge distributions, and we're going to have another method to do these called Gauss's law that makes these way easier. For homework number 2, we're just going to focus on one-dimensional and two-dimensional charge distributions. And I'll tell you what they are right now. I'll kind of give you an overview. The overview of what I'm going to do is I'm going to start with a finite line charge. And then I'm going to extend it, make it an infinite line charge. Those will be examples of one dimension. Then I'm going to do a ring of charge, and I'm going to then fill in the ring to make it a disk of charge, and then I'm going to take a disk of charge and I'm going to extend its radius to infinity to make it an infinite plane of charge, and those are going to be my two-dimensional charge distributions I look at. So what I'm going to do is I'm going to do them in order from here to here. The progression is not necessarily going to be from easiest to do the math to hardest to do the math. In some ways, the first one is one of the harder ones. So if we seem like we're kind of jumping in the deep end, just kind of hold on for dear life, and you'll hopefully get the hang of it. But there's a certain logical progression to not from easy to hard, but just sort of in terms of how we're building up the charge distribution. And I should mention that all of these, the results end up on the exam equation sheet. On page 1, in the upper right-hand corner, can't miss it, all of these results end up there. And you can just use them. You don't have to justify them whatsoever on the homeworks or exams or anything. Just use them, okay? So that's kind of the progression that homework number 2 follows. There's some other stuff at the beginning, but I'm talking about the continuous charge distribution stuff, those problems. So the progression is that the first set is going to be simply just use the equations. So don't have to reinvent the wheel. The results that we come up with here, just use them. You'll be there all day if you try to rederive these on every single problem. Just use them, okay? That's it. You still have to know how to use them, but don't try to integrate them from scratch. So you might ask, if you can just use these results, why would you bother watching these videos? You just use the equations. That's all you need to do. Well, the reason I want you to see how I do these is first to understand the techniques, so that in the second set of problems toward the end of homework 2, you're going to do your own integrations. So you need to kind of know how the process works if you're going to then do your own integrations of different charge distributions. And by the way, as I'm going through these, there'll be kind of little asides where I say, oh, you know, if you're doing a homework problem, oh, this is what you would do, but okay, back to what I'm doing, but I'll kind of give hints and just kind of show you how the homework problems tie into those. It's oftentimes in the middle of one of these derivations, it's just kind of taking a left turn instead of a right turn at some point. So that's kind of how homework number 2 is going to progress, and I will put these derivations in their own video or videos, but this is kind of just the background of what I'm going to do here.